So we have the integral over c of y times e to the x times z ds, where c is a line segment from 0, 0, 0 to 2, 1, 3. All right, well, let's write down the correct formula, the generic formula, so I'll do it over here. If you want to integrate over c, f of x, y, z ds, what's the, sorry, that should be a little s right there. What's the computational formula? In other words, what's the differential? That's what you need to know. That's equal to the integral over c. F has got to be in terms of, in other words, x, y, and z have to be in terms of t, right? We're getting this to a single integral, which means everything's in terms of a single parameter. So we got to come up with a parameterization. That's one thing. But what's the formula? It's f, everything in terms of t. I'm not going to write all that out. And then what's ds? Magnitude r prime of t dt, right? So I'm really going to emphasize the differentials. If you know that ds is the magnitude of r prime of t dt, well, that's very helpful, right? Knowing what the formulas for the differentials. And then realizing if we're integrating over a single curve c, that means we've got to put everything in terms of the parameter that the curve is in terms of t, usually we say. All right, so that leads us to the next part of the problem, parameterizing the curve. Well, in this case, the line segment. We know how to do that. Parametric equations of a line, right? That's old stuff. Do you see why this last chapter is awesome? You get to review all the other stuff you've done in the whole class. Or if you're a negative glass half is empty kind of person, that's why this chapter sucks. But no, you have to be glasses half full and say, we're reviewing everything. I'm not going to have to study much for the final. We're reviewing everything. Of course, that's not true. You do need to study a lot. But you don't, at least you're reviewing as you go. Okay. So let's review the equations of a line in space, parametric equations. It has direction vector A, B, C. So we call that V back in the first chapter. And it goes through x naught, y naught, z naught. So generically, x is equal to something, y is equal to something. What are those somethings? X is equal to x naught plus at. Remember, this guy is like 3 slopes in one. Isn't that a neat way to think of it? The vector v, the direction vector, takes over the role of slope, and each of its components actually becomes slope in the individual parametric equations. It contains like 3 different slope values in one. And then what would y equal? Y naught plus bt. And then z naught, z is equal to z naught plus ct. Yeah? All right, so then in this particular case, well, we've got to do something first before I can fill these in, but not a whole lot. What's the direction vector? 2, 1, 3, yeah. Because remember, if you think of 2, 1, 3 as your tip and 0, 0, 0 as your tail, tip minus tail, oh yeah, 2, 1, 3, right? And then what makes sense to, what point are you going to pick as your x naught, y naught, z naught? 0, 0, 0, yeah. Don't be silly and pick the more complicated looking point. Really, it's the first one you want to pick to get it to work out nicely as far as what t values give you your beginning point and your end point. So it's the first point in the parameterization because it's a line segment. It's not a full line, right? So it's the first point where it's the beginning point of your line segment. Okay, so x naught is 0, y naught is 0, z naught is 0. So fill in, what do we get? X is equal to 2t, y is equal to t, just 1t, and z is equal to 3t. Or r of t in component form is 2t, t, 3t. Right? Looking at the right-hand sides. Now check it. Well, before you check it, what is t going to have to range between? This part gives us our limits of integration. 0 to 1 should do it. Check it. If I plug in 0, certainly I do generate the point, the beginning point 0, 0, 0. And if I plug in 1, certainly I do generate 2, 1, 3 as my endpoint. It works. And it'll work every single time if you do it that way. If it's a line segment that you're integrating over. So this is truly a line integral, I suppose. All right, we're not quite ready to fill in this formula, but what does this formula tell us to find? If you look at the innermost grouping symbol, which would be the magnitude bars, and inside the prime notation, you got to find R of t. Got it. Then what do we do with R of t? We take the derivative. Let the notation be your guide. So R prime of t is equal to what? 2, 1, 3, the direction vector, which makes sense, right? Everybody okay with that? What do we do with that? Now you work your way out from the innermost grouping symbol, if you consider the prime a grouping symbol, R of t, the whole thing prime. Now you take the magnitude of it, and R prime of t becomes square root of what? 4 plus 1 plus 9, square root 14. Almost there. So then what does this integral become? The integral from what to what? 0 to 1. Magnitude R prime of t, root 14. Yeah? dt. What did I forget? Yeah, okay. Now, what does the function become? So that, if using the generic notation, the function is the f of x, y, z. What do you have to do with the function? You've got to plug in the x, the y, and the z. What gives you the x, the y, and the z? The parametric equations, right? Remember, you're integrating over that line segment. So on that line segment, x is equal to 2t, y is equal to t, and z is equal to 3t. So you plug, okay, so what does this become? T to begin with, right? Oops, let me switch here. So y is t, so I filled that in for t. E to the x times e, 2t plus 3t would be 6t squared. Yeah, that looks better. We knew it had to be more than just root 14t, right? Okay. Okay, but what are you going to do with that root 14? Pull it out. And then we have to think about, how do we integrate t e to the 6t squared dt? Going to be a U-Substitution, right? This is another one of those where if you're actually making the substitution, I think it's the hard way. You think about the substitution, which would be the exponent, right? You think about the du. What would the du be? 12t dt, right? And then you don't actually make the substitution. You put in what would make the perfect du, which is the 12. But then what do you have to do? So we have the 12t and then dt over here. So we have our perfect du, and then we divide out by 12, right? The net effect, we multiply by 1. And so what is actually, if you were to make the substitution, what would the integrand be then? It would just be e to the u du, right? Okay, we know how to integrate that. So we have the square root of 14 over 12. Don't forget that. Well, just what? E to the u is... Does everybody agree with that? Because if you actually, again, if you actually make the substitution without the limits of integration, it becomes e, this part is e to the u, and then 12t dt is du, so it really is that simple. So you integrate e to the u, it's e to the u. Oh, but u is 6t squared. So you avoid the middleman of making the substitution. Oh, but then we have to evaluate that, right? From what to what? 0 to 1. And what do we get? So root 14. Okay, so times e to the 6th minus 1, because when we plug in 0, we get e to the 0, right? Minus 1. Okay.